We are studying a design decision that is implicit in the way the internet works today, which is where packet repairing should be performed. And we have seen that there are two philosophies. And okay, I've lost my battery here. There are two philosophies. On the left, doing it end-to-end. This is what we have seen TCP does. On the right is repairing locally, hop by hop. This is what Wi-Fi does, for example. And what we would like to understand is whether one or the other should be done. And we have seen that there are reasons for doing both. There are reasons for doing end-to-end and reasons for not doing end-to-end. The reason for doing end-to-end is to keep things simple. We don't want routers to be involved in repairing packet losses. So perhaps it's okay for Wi-Fi base stations, but routers that are in the middle of the internet, perhaps we would not like them to do that. So what we'll do now is try to understand from a theoretical viewpoint why one should do one or the other. So it has to do with capacity. The goal of repairing losses is eventually to make sure the information gets through. And as a first metric for measuring how good we are, we can measure the throughput, how much information we're able to carry. This is what information theory does. And a very simple result on which we concluded last week is that if I have a channel with a nominal rate of capital R, bits per second, or packets per second, or bytes per second, that drops in average a fraction p of the packets, then the useful information we can carry through this channel is R times 1 minus p. Or more precisely, this is the capacity in the sense of information theory, which means that you can approach that rate as closely as you want. This is a bit the theoretical result in the sense that it does not say anything about the delays. But we can see that this is in fact what the protocol like TCP does. TCP will in fact replace only the packets that are lost. So in practice, it will approach that capacity. But that's not so much our question. Our question is, should we do things locally or end-to-end? So let's analyze first the capacity of a hypothetical simple example. I'm assuming here I have a long TCP connection, for example, that goes through many hops. And I assume, to simplify, that there is a same loss probability on every link, and even assume that the loss probability is such, the loss events are independent. What is the capacity of this channel? So the channel is the communication channel between the two ends, between A and B. What is the capacity of the channel when we lose in every link a packet with probability P? I'm also assuming all the links have the same rate, which is capital R. So here I'm assuming I'm doing hop by hop recovery. Like in Wi-Fi, I'm assuming every link, when it sees that a packet is lost, will ask the other end of the link to retransmit it. So for example, if a packet is lost between R3 and R4, R3 and R4 somehow will have a mechanism to detect it, and R3 will retransmit it. That's the assumption that's made here. With this assumption, what is the capacity we can get out of this channel? The majority is A, but the majority is not always right. The correct answer is B here. A looks like a familiar formula, so why not? But if we do hop-by-hop recovery, the capacity of one of the links is R1 minus P. So it's intuitively simple to admit that if you concatenate a number of links that have the same capacity, then the capacity of the end-to-end concatenation is the same, right? It's a pipe fluid engineering thing. If you have a pipe that has a certain diameter, if you put a connection of pipes that all have the same diameter, then the throughput is given by the diameter of the pipe. So it's the same here. So the capacity is R1 minus P. The other formula that the majority of you thought was the correct answer is in fact the formula we have if we do TCP or end-to-end recovery. Because if we do end-to-end recovery, the probability that a packet is not lost is given by the product of the probabilities, if we assume, like we did, that the loss events are independent. Therefore, the probability that the packet is lost is 1 minus this, and the capacity of the path is therefore, by the formula, R times 1 minus Q, this formula that we have here. Of course, if we apply this to a large k, large number of hops, 1 minus p to the power of k is exponentially decreasing with k. We see that here if we have 10 hops, and if we assume we have a packet loss rate of 5%, then the end-to-end capacity is 0.6. The capacity, if we do end-to-end recovery, like we do with TCP, will be 0.6, whereas if we do a hop by hop, it will be 0.95. If it's 10 to the minus 4, the end-to-end, the capacity with end-to-end is 0 with 3 nines, and with hop by hop with 4 nines. Well, this slide is exactly explaining the trade-offs and why things are in the internet. We see on the top, we have a loss rate which is not very large, but still embarrassing. It's a loss rate that will have a visible impact on your quality of service. You lose 5% of the packets, 1 out of 20 is lost. Then we see that if we do end-to-end retransmissions, then we lose 40% of the capacity, which means the capacity will be much, much less. We have lost, compared to 95%, we are at 60. So roughly speaking, 1/3 has been lost. So in a case like this, if a loss rate is not small, and 0.05 is not small, but it's not the worst, if you get much larger, 10, 20%, then of course the capacity will dramatically decrease, will be practically 0. So if we're in the top case, we should not do only end-to-end recovery. Right. Because if doing that, the capacity, the performance, when we download things over the internet, will be very bad. So if I download things from a faraway destination, on every link there's a probability of 5 or 10% that it gets lost, then in practice it will be very hard to transmit anything. The capacity will be very small. So if you have lossy links, you should repair the losses locally. That's the take-home message. This is why on Wi-Fi we do that. Wi-Fi being radio and being highly stochastic, highly random, we can't guarantee that the performance is very good. So if there are losses, we will try to retransmit at least locally. If we are in the second case, where the loss probability is very small, that kind of loss probability is typical of cabled system. Switched Ethernet, if we ignore losses due to buffer overflow, but those are the losses due to propagation errors or copy errors inside routers and bridges, then we see that we don't really care. I mean, going to 3 nines or 4 nines is a minuscule improvement. So the complexity of being hop by hop is not worth it, doesn't bring enough benefit to be justified. So this is how the TCP-IP architecture solves the problem. If the losses are not so rare on a link somewhere, then you should repair the losses locally. And the best place to do that is at the MAC layer, because the MAC layer is specific to the technology of the link, whereas IP is not. An adjacency between two IP routers at the IP level is not aware of whether this is over a long distance optical fiber or a local Ethernet link or a Wi-Fi. This is not visible to IP. So the correct place to put that is in the link layer, the MAC layer, layer 2. And this is what is typically done in all internet systems. Of course, we still need to repeat packets that have been lost at the transport layer, because even if we repair locally We are not guaranteed to always repair all losses because there's a trade-off between repairing and delays. If you transmit a packet over Wi-Fi and it fails, then you will retransmit. If the retransmission also fails, perhaps you will retransmit again and perhaps even a third time, but that will probably be it. If after a small finite number of retransmission it fails, then you drop the packet because perhaps there's shadowing, perhaps something wrong has happened that will come back again later, but you don't want to retransmit forever because while you are retransmitting, you are keeping the channel busy for you, so others cannot transmit on Wi-Fi. So this is how things are organized in the internet. And this is our conclusion for the transport layer. So we have seen that the transport layer in TCP-IP exists at least in the simple approximation in two flavors, TCP and UDP, and those are the two flavors that are visible to us when we program using standard socket libraries, for example. There are other transport layer protocols that provide reliability. There has been a large number of them that have been proposed in the lab. We will use WebSockets, which is not a transport layer, but really application layer framework. Because TCP, which is the standard way of providing reliability, has a number of drawbacks, let's say. The fact that it is stream-oriented makes it a fairly low-level primitive. So, for example, when you transmit messages with TCP, you need at the application layer to do something about it. This is what WebSockets is doing, for example. Voila, that's all for the theory part of the transport layer. Any questions on this?